regular link. There we go. Tuesday at 3 o'clock. Today's Tuesday, so I'll be there today. And then also we have Brandon, our math tutor, math intervention specialist. He's available all week long at different times throughout every single day. So take down this info if you want even more extra time to just get help on this math stuff, on anything from class. Here's his email. All you got to do is write him an email or a note on Google Chat and say, hey, my name is so so. I'd like to work with you sometime today or this week. When can we do that? And if you want help setting up that meeting, just let me know and I can help you set up a meeting with Brandon, okay? Okay. All right, so today's lesson in Admentum, it's the second lesson in Unit 6. So just a reminder, we're in Unit 6. Hunter, I think I still need to add you. So at the end of class, I'm going to add you to the Unit 6, to Math 2B. So sorry about that. Just stay with me for class today, and then we'll have you in there so you can do this work today. Okay. Everyone else should have access, I think. Let me know if you don't. So today's lesson is called Similarity and Similarity Transformations. So yesterday we started dilations. And dilations means we take the first figure and we either enlarge it or we shrink it by multiplying the figure's sides by some number. And so that's what we started with yesterday. We're going to be doing more of that today, but we're going to be adding in this idea of similarity. So, what does it mean for similarity in math and for our different figures? Similarity means that two figures have equal angles and proportional sides. Proportional sides, this just means that all the sides have been multiplied by the same scale factor like we were doing yesterday. In other words, one of the figures is a dilation of the other. So you've taken our original figure and maybe blown it up to a larger size, but all the angles are still the same, just like we saw yesterday. So there'll be a correspondence between every angle on the figure. And there'll be proportional sides. So, for example, if our original figure on the left, our small guy, was links of something like 3, 4, and 5, maybe we blew up the figure times 2. So if I doubled all the original side links, what would that make my new side links? Can anyone help me out with that either in the chat or with your mic? If we doubled the original side links using a dilation like yesterday, what would make my new side links be? Any thoughts? Anyone want to take a risk on this one?
I'm sorry, what was your question?
My question is, can you see my red drawing or is that showing up on your screen?
Yeah, I can see that.
Okay, so the question is, thank you. The question is, if we started with the little figure on the left, 3, 4, and 5 side links, and then we did a dilation of times 2,
Mm,
what would that make my new side links be on the right side?
bigger.
Bigger, and can we tell by exactly how much if I know the scale factor is 2 in this case?
So it'd just be like double.
Exactly. Exactly. So in this case, because it's times 2, we're doubling. So the 3 side turns into a side of 6, for example. Oh, Antonio, high five to you from far away. In the chat, Antonio threw in 6 and then 8 and then 10. Where did he get those numbers from? It's the original side links all times the scale factor. So this is just another example of a dilation like from what we started doing yesterday. So I wanted you guys to keep that in mind because we're going to be doing more of these. But we're also adding on a couple other moves, other transformations. And I want to look at those with you now. So I'm going to wait like 8 seconds, and then we're going to look at the new screen. If you need more time, let me know. And thank you, Antonio, and thank you, Aaron, for jumping in to help with that question. Okay, here we go. Now, let me see if I can get this out of the way. There we go. So we're going to be looking at a total of 4 different transformations in today's work. We'll be using different combinations of 4 different transformations, and here they are all below. So number 1, rotation. So to do a rotation, it's like starting with the blue figure here, original, and then we're rotating some number of degrees. Usually we rotate in these 4 different degrees. It could be 90 degrees, 180, 270, and then well, actually that's basically it. The fourth one would be 360, which is like rotating all the way around and ending up exactly where you started. So a 90-degree rotation is a quarter turn. 180-degree flips it around 2 90-degree turns. So it's like here plus one more. 270 is 3 90-degree turns. And then 360, we end up just going in a full circle. So it's a little redundant. So we actually don't use 360 too much. So we're going to look at this in action in just a moment to get a little better hands-on practice with it. Second transformation we'll be using is reflection. So this is simply kind of folding your image across some line. So here we see our blue image. And then the whole thing has been reflected across this line in the middle. And then we see its opposite. It's like mirror image on the right side here. So our ending image after doing a reflection. Notice that the 2 figures are a match, but they're not in the same like orientation anymore. So for example, I'm looking at reflection. The pointy edge right here, this vertice, this pointy edge matches up with this one on the right side. So when we're doing a reflection, all the angles are still the same. Notice that like I know we're not measuring it like fully here, but this pointy angle is a match for this one on the right side. So the angles are being preserved, just like we saw yesterday with our dilations. The angles themselves don't change, but the direction that the picture faces is changing because we're rotating it or we're reflecting it. Number 3 below is translation. And this is like a drag and drop kind of. With translation, it's kind of nice because the orientation is the same. So we can see the blue image and then the red image are in the same exact like location, or not location. They're in the same positioning. So this time the pointy edge and the pointy edge are kind of in the same place, like bottom left, and then again bottom left for that landmark. But it's been moved to the right by some number of units. So maybe they moved it, a certain number of units, 10 units, let's just say, for example. So when we're looking at two images on a graph, we'll be able to count how many squares, how many units it's been moved over. And again, we'll look at some practice in that in just a second. And then fourth is dilation. And this is what we started yesterday. So nothing new here, but this is the same as yesterday. And I want to keep that in your mind. Notice that in the picture here, we've got our point of dilation, dilated from the center or from the origin or from some point. And then starting from the blue image, going to the littler, smaller red image, it looks like it's been shrunk. So they must have multiplied by some fraction, like a half or a third, for example. Just like we saw on the last screen, starting with the original, multiplying everything by some scale factor, making it bigger or smaller. And again, I want to stress to you that the angles are the same. The side links have changed with a dilation. They're proportional, but the angles are the same. So I want to do two examples with you on finding the scale factor between a figure and its dilation. And then we're going to get some practice with using these other three transformations with doing rotations, reflections, and translations. Any questions right now? Concerns? Comments, please. No. Okay, that's all right. Make sure to take a picture of this or finish up your notes so you have an idea of these four different transformations on your paper for later. If you're doing your notes digitally on Google Docs, um, screenshot would be a good idea and put that into your notes so you have these four images for later. Okay, here we go. So let's look at two examples of just finding the scale factor because we're going to be doing this probably for every single like problem or question in today's mastery test. So example one, assume that JKLM is similar to PQRS. This symbol here means similar. So that means the angles are the same and that means the sides are proportional. We need that to be true to find um, the scale factor and find any unknown sides. So it means the sides are proportional. So basically, the two figures that we have on the right, what this is saying is they're similar to each other, and that means one is a dilation of the other. Okay, so it says find PQ. Find how long is P to Q, this segment right here. How long is Z essentially? What do we have given to us? What do we know for sure? We know that side QR is 6 units. We know that on the big image, JK is 10, and we know that KL is 15. Because the sides are proportional, that means there's some number that I could multiply the big image by to get the little image. Some scale factor. Maybe it's a fraction, maybe it's a whole number. It's something though, for sure. So if I'm supposed to find QP or PQ, if I'm supposed to find the little segment labeled Z right here, see how that's comparable to the side length of JK on the left. Now, how do we know that those two are comparable? We have to kind of match up the images visually to see which ones go together. Um, One that stands out to me is the diagonal side. Notice the 15 and the 6, KL and QR. These two go together. And that means JK, this littlest side, goes with QP, the one we're interested in finding. Another clue that we can use to match up the sides and know which ones quote unquote go together is the way the similarity is stated over here on the left. JKLM similar to PQRS. So the order of listing off those points matters. So for example, KL, the diagonal side, right here. I'm going to underline it on the left, KL. Well, what are the two in the center on the right image? The way it's listed is QR. So that means side KL goes with side QR. And also side JK, the first two, go with the first two on the other one, side PQ or QP. So the way it's listed is also telling us which two sides are, which sets of sides are proportional to each other and go together. So now that that's out of the way, okay, one more person's joining. So now that that's out of the way, let's try to find QP. So if we know KL is proportional to QR, KL is proportional or similar to QR. Well, what are the numbers? What are the lengths associated with those two sides? That's the 15 and the 6. So 15 times, usually we write little k for scale factor. I'm just going to write scale factor, the whole word's there. 15 times the scale factor, if we knew that number, equals 6. I'm just comparing matching sides together from one image to the next because we know some dilation made the small image from the big image. So 15 times the unknown scale factor is equal to 6. Well, if I solve this equation I've just made backwards, I'll go ahead and write it as S just to make it a variable, make it look more like normal math. So now I can divide both sides by 15. Remember on the left, 15 divided by 15, that cancels. That makes a 1. So we have S equals 6 over 15. That means 6 over 15, 6/15 is our scale factor. Also, though, side note, if we can reduce a fraction, let's reduce it, make it a little smaller and easier to work with. So I noticed that 6 and 15 can both be divided by 3, so I'm just going to reduce this fraction. So 6 over 3 is 2, 15 over 3 is 5. So let's call this our scale factor, 2/5. Circle that, box that so we don't forget about it. So how are we going to use this to find the missing side PQ labeled Z? How do we use this? Well, that means the side JK times the scale factor, which we found as 2/5, should give us QP. So now I'm basically saying this, JK times 2/5 equals the little side, QP. Plug in the parts we know. JK is 10. 10 times 2, and then 20 over 5 gives me 4. So that means PQ or QP, the side we were looking for, is 4. So we have to find scale factor by comparing two sides together, and then we use that scale factor to find the missing side. No worries. Thanks for rejoining. I'm glad you made it back. We can do this process we did because it says at the beginning, assume the first figure is similar to the second. It's telling us that they're proportional. So it's telling us that there is a scale factor that exists that we can go from one side to the next, one figure to the next. Okay. I have to move on. Any questions or concerns about this example so far, please? All right. Let's look at another question. And this again is just looking for a scale factor. So same kind of question as last time. This time though, the two figures are on a graph already. Get that out of the way. Okay, so it says assume triangle ABC is similar to triangle DBE. So we see the two like orange beige triangles, they're similar to each other. Find the scale factor to map ABC to DBE. Find the number that we can multiply the big triangle by to get to the smaller triangle. So this time we were given the two side links AC and ED. Those look like they are the ones that should go together. How can we double check? Look at the naming of those sides in the similarity statement at the top of the problem. AC, first and last letter. So that should match up with the first and last on the other one, DE. Perfect. AC is proportional to DE or ED, same thing. So that means side AC times the scale factor, just like last time, equals the smaller side that it's comparable to, ED. So let's plug in some numbers here. AC is 18.45 times, I'm going to shorten this to S again. So S for scale factor equals 11.07 for ED. Divide both sides by 18.45. Why are we doing that? To get S alone, to solve for scale factor. Okay. So we're dividing the 11.07 by 18.45. Let's see what we get. 0.6. S is 0.6. That's our scale factor. So if we multiply any side on the larger triangle times our scale factor of 0.6, it gives us the smaller triangle. So how do we do this? We have to find the sides that are comparable, and then we figure out what are we multiplying by to get from one to the other. It didn't tell us if which one of these was our original, which one was our ending figure. So I just said larger times this scale makes the smaller. Oh, actually, it did. I'm sorry. Look back. Find the scale factor to map ABC to DBE. So that means larger was supposed to be our original. Good. So I got lucky. Larger was original. do a dilation and it makes smaller dBE. New. Okay. Now I want to reiterate our goal for today, and then I want to look at the activity that they gave us in Edmentum. So we're going to do some more GeoGebra work like we did yesterday to get some practice using all four of these. Our goal today for this whole lesson is to be able to figure out what transformations out of these four options we use to make one figure match with the other figure. So we'll be doing dilations, but we'll also be rotating it, reflecting it, or translating it. I think the best way to learn this is just to practice it. We have to identify how they look like they match up and then kind of work backwards to see what steps we could take to make them match up. Now, to do this, in Edmentum, this is my view of Edmentum, is a little different than your guys' student view. We're in the second lesson right here, similarity transformations. I'm going to go to this tutorial. So you all have access to this, except Hunter, my bad. I'm going to add you in just a minute. So I'll do it now, Hunter, not wait till the end of class. I'm going to go to the first um, like activity that shows up in the tutorial for similarity and similarity transformations. So going here to the tutorial, it looks like it's page 6. So if you want, I'd like you guys to go to this. I don't need to give the link because it's the same thing you all have access to. So I'd like you all to go to the same tutorial. You can skip forward to page 6. And then I want to do this first activity together in class today. We don't have to do the whole thing. I'm not going to like require you do it all, but I do want you to do this first activity right here. Question 1 on page 6 of the tutorial, Similarity and Similarity Transformations. So they want us to open this Similarity Transformations like activity up in GeoGebra. So if you click on this blue link, the first one there, question 1, it brings us to this. So it looks like yesterday's. Same program, GeoGebra. And I know it looks kind of messy, but what we're looking at is our original figure ABCD. That's this one. And then step by step, we're going to look at the other ones. They have a black figure, the blue one, the green, and then like the darker red. And we want to find, can we match our starting? Starting is always A, B, C, D, E, this one, kind of brown orange one. Can we map that onto the other figures using our transformations? So I'll start the first one with you. And actually, um, I'm going to stop recording and I'm going to stop sharing so I can open up the class for one student. And then I want to do the first one with you. So right now, what I'd like all of you to do is to navigate to this section yourself so you can do it with me. So again, we are in Unit 6, Math 2B Unit 6, the second tutorial called Similarity Transformations. Click on the tutorial and click to page 6 and then open up this blue link, Similarity Transformations. You should end it here. This is where I want everyone to be. And just, I'm going to pause quick so I can open up the class for another student. Any questions? Go ahead and type them in the chat. Here we go. Okay, and now come back with me to my screen. I'm hoping everyone has access and you've been able to get to this part here. So this is the tutorial, Similarity Transformations. Now, again, I realize that this program is might be a little intimidating, especially the first couple times you use it. I was hoping yesterday would be good practice. And remember, yesterday I had taken away a lot of these tools, so it's just the ones we needed. So in this activity, they're all available. So it's a little busier. So work with me on this to get some practice. We'll be doing most of the same like functions over and over again. So that's good. So our first goal is to see if we can map A, B, C, D to this image F, G, H, I, J. And that's the small black one, F, G, H, I, J. So our first step every time we're doing these transformations is try to find a landmark, a point, a, a, a side or an angle, something that stands out to you that matches up. So for me, I'm going to zoom it in. For me, I think the smallest side, BC, right here, that should match up with the smallest side on my little figure, GH or HG right here. That looks like a match. How do I know? It's the smallest side on both figures. Our problem is ABCDE is not oriented the same way. It's not like we can just slide it over, right? We're going to have to do a rotation here or maybe a reflection. Um, I imagine taking the ABCDE and rotating it 180 degrees. Also, the size is off, and that means there's a dilation happening. So that's another thing. I think let's start with our dilation and make the sizes match. So how can we tell how to fix that and dilate the orange one to match with the black one? Let's we yesterday we did our dilation tool. I'm going to add a point at the origin so we can use that to dilate from. So add a point right at the center at 0, 0. And then I'm going to use the dilate tool. Let's see. Here's measuring, and here's the transformation. So we're going to be using this section a lot for all the different transformations. Dilate from point. So click on the whole figure, and then click on the point we just made. Oh, and I need to know the factor. I didn't figure out the scale factor. So cancel. So let's compare the two smallest sides. Let's measure both of those. Here's our distance and length measuring tool. So click on BC, and then let's click on GH. Okay, and that's measuring something else. So let's zoom this puppy in and then measure HG. Okay, so now we see BC is 1, HG is a half. So that means we've multiplied by a half. We've gone down from 1 to 0.5. So our scale factor looks like it's 0.5 itself. It's 1 over 2. So now we can do the dilation. Dilate, type in 0.5, that's 1 half. Cool. And now we see the dilation we just made. Here's our little guy. This should match up once we do a rotation and then maybe drag it across the screen using a translation. So let's do a rotation next. I'm going to rotate this 90 degrees and see if that lines up. So in our transformation tools, rotate around point, click on the little one we just made, and then click on the point. And then it wants us to type in our angle of rotation. Keep it on counterclockwise, and let's try 90 degrees. Here's my rotation of 90 degrees. Still not lined up the correct way. Let's do another rotation. Let's see, rotate around point, this figure, this point. Let's try 180 degree. Now, here's my result down below. Notice that the new figure we made is in the same orientation as the black figure we're trying to match it up with. So this is good. So our last step is to figure out how many units up and over do I move this. Actually, in GeoGebra, we're using vectors. So let me show you how to do that. Okay, so in the line tools on the left side is vector. So there's different ways to do transformations. Sometimes we just type in like up 5 and over 3. Instead of doing it by direction like that, we're making this vector line, kind of array, but it's called a vector. So to do the vector, I want to match up point to point what looks like it should go, what should be matched up. So again, my pointiest side is this A double prime 1, and that should go with F. So I'm going to click on A and make it match up to F. And if I could drag it along that line, it looks like it should end where we want it. And now let's do the actual translation. So translate by vector, click on the figure and then the vector line. Boom. And there it is. So now I've got my starting figure finally transformed and matched up perfectly on top of my ending figure. And we did like 3 different moves. So I'm going to go back to the Edmentum. They want us to write the sequence of rigid motions or dilations. This just means we're going to write out what we did. So first we did a dilation. Zoom in. See this? So we did a dilation of 0.5. Then we did a rotation of 180 degrees. Last, we did a translation along the vector. And I'm going to even look up and see how many units up and over that was. So it went up 1, 2, 3 squares and over 1, 2, 3, 4, 5, 6, 7. Up 3, right 7. So that was exactly what we did. Up 3 and right 7. So we had to start by identifying what looks like it matches up, and then one step at a time work to move it there. So I'm going to like undo and delete all my work. Actually, I'm just going to reload it so we can try the next one. So now we want to try to make it match up with KLM and P. Starting with the ABC one, we're going to try to make it blown up to this blue figure here, KLM and P. Good news, it's already in the right orientation. So if I want to start with A, B, C, D, E and end with K, L, M, and P, the blue one, are we going to be enlarging it or shrinking it? Does anyone see that? Do we want to enlarge or shrink to go from orange to blue?
Enlarge.
Awesome. Enlarge. How can we find out how much to enlarge? Any ideas? Any thoughts? First thought. We need to know some comparable sides, right? So we've got lots of choices. We could do the AB to KL. We see those they look like they're supposed to be a match. We need to measure them. So we can count the units if that's possible on the graph, or we can use the tool here to measure distance or length. So click on AB, that's 2 units. Click on KL, 4 units. So this looks like it's times 2, starting from 2, ending at 4 times 2. So let's start by doing that. Let's dilate ABCD times 2. Remember, to do a dilation, you have to have a point of dilation. So I'm going to do it from the origin again. All right, dilate ABCDE by this point and a factor of 2, scale factor 2. Oops. Okay. Okay, cool. I know they're kind of covering each other, but if we move our red one or our ABC dilated, move it down and over, I think we'll get it to line up. So let's try another vector. Let's match up the A prime with the top left corner over here on blue, and then we'll do the translation. So click on the original figure and now the vector line. Okay, it's unfortunate that they made them on top of each other, but I think we did it correctly. We've got it lined up. All right, so this time we did two moves. We did a dilation of 2, and then we did a translation on the vector. What were the exact directions the vector did? It was down 1 square and right 2 squares. Down 1 and right 2. That's the idea here. It is going to take some trial and error to get it to work properly, especially when we're doing rotations. So what I would suggest is try doing 90, try doing 180. If it doesn't work, try the next number, try 270 until it lines up the way you want it to look like it's lined up. Okay, let's see, it's almost 11. So QRSTU. All right, so at this point, here's what I'd like to do. I want you guys to use this tool in the tutorial to practice doing your transformations, just like we did here. So I did the first two. It's possible that the figures won't line up properly. So maybe that means if you get one like that, that means that the two figures aren't actually similar. Maybe they look like they are, but if the numbers don't line up properly for all the sides, that means they're not similar. So in that case, you'll write not similar if you find one like that. So practice those. Practice doing these first two as well. So just try it on your own. You can always look back at the video later if you need help on how I did that and use these different tools. The mastery test for today is going to be very similar to what the problem was like in this tutorial. So here's one example from our mastery test today. We see a graph, we see two figures, not too cluttered like the activity was. It says we want to the transformation that maps polygon PQRS onto EFGH. So that's the larger going to smaller. In the drop down here, our choices are rotation and reflection. And then we have to figure out the dilation with a scale factor of what? Of some number. So to get the larger figure to map onto the smaller figure, it doesn't look like a reflection would work. If I reflected it along a line in the middle of them, then the resulting larger figure would look like this. And we can see that it's not positioned and oriented the right way. But if we were to rotate it, if we had the ability to rotate this, pivot around some point, then we could get this diagonal QR to line up with the diagonal FG, which is what we want. We want it to be able to line up that way. Then compare some other landmarks. Small side PQ should match up with EF. Cool. So that looks like it would if we could rotate this 90 degrees, 1/4 turn. And we have to find the scale factor. So to find the scale factor, let's compare two proportional sides. So PQ from here to here, how many units is that? Now we'll have to count them on the graph. 8 to 12, so that's 4 units tall. And then EF is 14 to 16, 2 units. So large figure times scale factor gives me the small figure. So that means 4 times S is 2. So scale factor is 1/2, 2/4, 1/2. So just like we were doing earlier. So every question that I saw is going to be dealing with scale factors. So every time we're going to be needing to compare sides and figure out what am I multiplying by? Is it a whole number? Is it a fraction like a half? And this is how we can do that. All right, we have time for one more. This one, when you first look at it, I'm sure you're thinking it looks really confusing. Slow down. Make sure you know what it's asking and what information we have to use. Okay, ABC and PQR are similar triangles. ABC is dilated by a factor of 1.25 and rotated 45 this many degrees counterclockwise from point B to make PQR. Okay, so basically ABC is rotated 45 degrees and it makes PQR. And it's also been scaled by a factor of 1.25. So it gets a little bigger. Then they tell us the side lengths. AB is 5 units, BC is 4.2, and AC is 4. Match each side of PQR to its length. So even though they gave us all this information about rotating it, that doesn't apply to us. All we need to do this is the scale factor, and they told us that is 1.25. So PQ matches up with BC. No, PQ should match up with AB. There we go. How do we know? Look at the statement, the similarity statement. So first two, AB matches up with PQ. So PQ here, AB times the scale factor equals PQ, same formula we've been using. And if we know AB is 5 originally, and the scale factor is 1.25, that can tell us what PQ is. 6.25. So then we can match it up like so. So sometimes they give us more information than we need, like they did here. So some of the overly confusing stuff, depending on what they ask for, we can shed it. We can cut it loose. We don't even need to know about this rotation of 45 clockwise. All we needed to know is the sides of the original, and they told us scale factor, and that helped us find the sides of the ending figure. Okay, before I let you guys go, I need to take your attendance and I need to ask any questions or concerns right now about the activity and momentum or the examples that we did earlier or this one.
I have a few, but I think I'm gonna wait till next class because they're really long questions.
Right in. Don't wait till next class. Ask now.
Well, that's the thing. Like, I'm kind of confused about my own question. I'm still trying to get used to this.
Okay. I want you to, I appreciate you telling me. I want you to today, after class, go on and watch yesterday's with dilations because yesterday we started just doing the dilations. So it's a little bit easier to start with just one thing, I think. And then you can look at today's work again.
Okay, what was the name of your YouTube channel again?
What I want you to do